Stokes' theorem. Let S be a piecewise smooth oriented surface with a boundary that is simple closed curve C with positive orientation. If F is a vector field with component functions that have continuous partial derivatives on the open region containing S, then they just had these two in the middle, that F dot dr is equal to the curl of F ds. Now I've added all these other ones in, but they're all related to each other here, and you can see that the curl of F is actually del cross F. It's also this one here, the curl of F when I plug in my RUV. Those are all the same. And then here, when I look at NDS, that's this part here. But N is also TU cross TV. And I just wanted to give you all the practical formulas in which you'll see all of these. And the only two that are different that we've seen, and this is honestly the other side of the integral, this is the single integral, and this one is equal to the integral of F when I plug in RT dotted with R prime T dt. So we know those are related just from previous sections. But all the other ones are the double integrals that it's actually equal to because of Stokes' theorem. Now, one way to look at this is the extension of Green's theorem that's only two-dimensional. Stokes takes it to the third dimension, where now we're talking about vector fields on surfaces in 3 dimensions instead of just the 2. Now, if you look below here, this says for the following exercises without using Stokes' theorem, calculate directly both the flux of curl F dot n over the given surface and the circulation integral around its boundary, assuming all boundaries are oriented clockwise as viewed from above. So this number 334 here says fxyz equals 4y I zj and 2yk, and c is the intersection of the sphere with the plane z equals 0, and using the outward normal vector. So what this is telling us is it's really honestly telling us to use this formula, because honestly we don't use the integral of f dot dr. We always go to something practical that we're going to use. The f dot dr is just a generic way, a general way of thinking about the circulation, work, whatever we want to call it, but it really comes down to the single integral of f when I plug in RT, R prime T dt, dotted with that. So that's really where we're going with this problem. And that's not using really the Stokes side of the theorem. Well, we can, and that's the beauty of it. I can use either one of the sides here with Stokes' theorem, and that's what gives me the ability to say, hey, this single integral actually equals all of these double integrals, which hopefully you see that they're all the same. And I just wanted to give you all the different forms in which you see it in the book. So anyways, let's get started with this one. So we're going to need an RT. We're just talking about this C here. Okay, now the C is the intersection of the plane and the sphere. So now if I just take this equation here, x plus y squared, and plug in a 0 for z squared, or 0 for z, I should say, I end up with this, and this gives me the equation x plus y squared equals 4. So this is really the circle of radius 2. So where my mind goes right away for my RT is my RT goes in the direction of polar here. Because what I'm going to say here is, since my radius is 2, I'm going to write 2 cos t, 2 sine t. Now again, keep in mind what this also said here, that we're oriented clockwise as viewed from above. So with the picture below here, if I plug in 0 for my t here, so cosine of 0 is 1, so that would be 2. And then the sine of 0 is 0, so that would be here. And then my next point would be pi halves, so when I plug in pi halves for t, my x is going to be 0 and my y is going to be 2, so I'm going to be at 0, 2, so it's going to be here. So this shows me I'm going in this direction. But notice what this says. This says, around the boundary, assuming all boundaries are oriented clockwise as viewed from above. So that would be counterclockwise from above. So I can just switch these around. So I'm going to write it this way. Now when I examine this, if I put my 0 in for my sign, I'm going to get 0 here and 2. So my first point would be 0, 2. So that would be here. And then I would put the pi halves in, and that would be 2, and that would be 0. And that would put me down here. So now this would be going in a clockwise direction from above. So this is the RT that actually does what it's asking us to do here. So we're going to use that RT for this problem. So keep in mind what we're going to use here. This here is going to be the formula we're using here. So we're going to have to take that vector field, find r prime t, and then dot those together. And after we plug in all the t's in for the x, y's, and z's in the vector field. So that's where we're heading to. So let's find that r prime t. So r prime t is going to equal 2 cosine t, comma, negative 2 sine t. So we're going to set up our double integral here. Oops, not a double integral, excuse me, a single integral. And that's going to be from 0 to 2 pi because my t is going to go all the way around. All right, and then we're going to have our f here. So I'm going to write my components here. And I'm wondering if I should write them up top first. I'll write them up here first to get them all in. So I got a 4. And then my y is 2 cosine t. So 4, cosine t. There's my first one there. And now notice I ran across the z here. Even though we're looking at x squared plus y squared equals 4, we're thinking of this as three-dimensional. So what we'll have to do for this one here is we're going to have to extend this a little, and we're going to have to add that third component in. And that third component being 0 for the z. So just keep that in mind to make sure the dimensions match. If it was a z equals 1, then that would have been a 1 on the end there. So it just turns out to be a z there. Even though we're looking at it on the xy plane three-dimensionally, I can write it as a two-dimensional RT or a three-dimensional RT with the z being a constant. Okay, so anyway, so then that means my middle term, since it's z, is going to be a 0. And then I have 2 and then my y. So my y being 2 cos t. So then that's going to make this not a 2 anymore, because it's times 2 there. So that's going to be 4 cos t. I did forget something here, and I just noticed it as I wrote that 4 there. If I look at my first number here, that shouldn't be a 4 there. It's 4 times y, and y is 2 cos t. So that actually should be an 8. Okay, I'm glad I caught that before I got started with this one. So that's going to be my f with my t's inserted into it. So that's a FRT that I see there. So that's going to be 8 cosine t, comma 0, comma 4 cosine t, dotted with r prime t, which is 2 cosine t, comma negative 2 sine t, comma 0 dt. So that's our design, that's our setup here. So now we're going to multiply, I should say dot product, these two vectors together. One thing that's kind of nice here, that first one's going to be 16 cosine squared t. And then the middle ones become 0, and the last ones become 0. So that's all I have there, and that dt. So now if I wanted to do this by hand, I would just use that identity here, the 1/2 cos 2 theta plus 1 equals cosine squared theta. And just sub that in there and work it out. All I did for this one here is I just wrote the answer out. And that's what I wanted you guys to see. I don't want to spend too much time on the integrals for this one. I end up with 16 pi once I plug it in. So that's our answer for this one here. And again, this isn't using Stokes' theorem. This is just using what we had before, the integral of f rt dotted with r prime t dt. And that's what we end up with. The next problems we're going to be dealing with the double integral of the curl. But realize Stokes' theorem is both sides of this. So I can go one way or the other. And the beauty of it is that they're equal. So I can talk about just the boundary of the surface. So for instance, when I had this here, I had this circular thing here. And I could look at the vector field on this by just using the boundary, that C there, or I can do it by reparameterizing or parameterizing the surface and just integrating with a double integral. And that's honestly the beauty of this theorem. And we'll be getting into those in the next video.